Hey everyone, and welcome to this explainer. Today, we're diving into something absolutely mind-blowing. We are going on a journey to explore the absolute pinnacle of human engineering. We're looking at machines that don't just, compute things, they practically look into the future. That's right, we are exploring the world's most powerful computers. Now, I want you to just think about this for a second. What exactly drives the most complex simulations in the entire world? I mean, when humanity needs to model the global climate, or test the safety of a nuclear arsenal without actually detonating a weapon, or map out the behavior of a novel pandemic virus down to its literal atoms, your standard computer simply isn't going to cut it. The stakes here are unimaginably high, and the sheer processing power you need to meet those stakes, it's truly mind-boggling. All right, so here's our roadmap for today. First, we'll look at the era of supercomputers. Then we'll check out the X-scale giants, followed by the global powerhouses. And finally, we'll uncover the shared DNA connecting them all. Let's get right into it. Part 1. The era of supercomputers, far beyond the ordinary PC. So let's get our definitions straight right off the bat. When we say supercomputers, we are definitely not talking about a beefed-up version of the laptop sitting on your desk. We are talking about massive warehouse-sized systems dedicated entirely to the bleeding edge of science, artificial intelligence, climate modeling, and nuclear simulations. These things are custom-built, highly specialized engines designed for one thing and one thing only: solving humanity's most impossibly complex problems. Whether it's training next-gen AI, predicting weather patterns decades in advance, or running highly classified nuclear tests, these machines are operating on a level of math and physics that's honestly kind of hard to even wrap your head around. Moving on to part 2. The exascale giants, the top of the American podium. Okay, when you look at the raw numbers, it really puts this unimaginable power into perspective. In this tier, we measure performance in something called exaflops. And just to be super clear on what that means, one exaflop means the system can perform 1 quintillion calculations per second. That's a 1 followed by 18 zeros every single second. Right now, 3 massive US titans completely dominate this space. You've got El Capitan leading the pack with an estimated peak of 1.7 exaflops. Right on its heels is Frontier at 1.68, and then Aurora safely crossing that insane 1.0 exaflop threshold. Now, what's really interesting is how these two leading AMD-powered heavyweights divide up their massive workloads. First, you've got El Capitan out at the Lawrence Livermore National Lab in California. It uses advanced AMD Instinct and EPYC hardware to focus heavily on national security and nuclear weapon simulations. Meanwhile, over in Tennessee, Frontier holds the historic title of being the very first stable exascale supercomputer. Using a similar hybrid setup, it tackles vast climate simulations, material sciences, and high-performance AI. But AMD isn't the only player in this game. Enter Aurora, over at the Argonne National Lab in Illinois. This is Intel's massive counterpoint. Aurora relies on a completely different architecture, using Intel Xeon CPUs paired with Intel's Ponte Vecchio data center GPUs. And why does that matter? Because Aurora is specifically optimized for large-scale generative AI, along with deep simulations in physics and chemistry. It's basically a slightly different philosophical approach to hitting that quintillion calculations a second milestone. Actually, before we move on from the US, we've got to pay some respect to the slightly older, but still incredibly vital, previous generation. Systems like Summit and Sierra operate in the hundreds of petaflops, which is basically the tier right below exascale. Both of these rely on a pairing of IBM Power 9 CPUs and NVIDIA GPUs, and definitely don't let their older specs fool you. Summit, for instance, performed literal world-changing tasks. During the height of the pandemic, it ran massive COVID-19 simulations and rapid drug development models. Sierra handled crucial virtual weapon testing for national security. They absolutely laid the groundwork for the exascale era we're in today. All right, part 3, global powerhouses, a race around the world. 10,500,000. Just let that number sink in for a second. So what is that massive number? Well, it's the number of distributed computing cores packed inside China's Sunway exascale prototypes, located at the National Supercomputing Center in Wuxi. While the US partnered up with commercial giants like AMD and Intel, China took a radically different approach. They built processors entirely of their own homegrown design, over 41,000 of them, to network those 10.5 million cores together. Running on a modified Chinese Linux operating system, this beast reaches that coveted 1 exaflop mark, completely dedicating its power to climate tracking, deep ocean modeling, and advanced scientific research. And this global race just keeps going across Europe and Asia with 3 other incredible powerhouses. First up, Lumi in Finland. Hitting up to 580 petaflops using AMD architecture, Lumi is famous for its energy efficiency. It's powered entirely by renewable energy, which is a massive achievement when you think about how much electricity these things guzzle down. Next is Leonardo in Italy, pushing roughly 420 petaflops by combining AMD CPUs with NVIDIA A100 GPUs to focus on aerospace engineering and medicine. Finally, we have Fugaku in Japan. This one actually held the title of fastest in the world a few years ago. Running at about 442 petaflops, Fugaku uses a really unique ARM-based Fujitsu architecture, and it's been absolutely vital for Japan's medical research and highly detailed natural disaster modeling. Which brings us to part 4. The shared DNA, the secret behind the power. Okay, so here is the ultimate plot twist. We've talked about all these different countries, totally different hardware setups, AMD, Intel, IBM, custom Chinese designs, ARM. You would think these machines have absolutely nothing in common, right? Well, they do. The crucial shared link is Linux. Despite the wild variations in location and scientific purpose, virtually every single one of these world-class supercomputers relies on customized variants of the Linux operating system. Whether it's a heavily modified version of Red Hat, SUSE, Cray OS, or custom national software stacks, Linux is the quiet, shared DNA that makes managing millions of computing cores actually possible. And beyond just the OS, there's actually a standard anatomical structure that pops up across all these exascale systems. We're talking hybrid architectures, pairing traditional CPUs with massive GPU arrays, which results in hundreds of thousands to literally millions of cores working in perfect sync. They need up to actual petabytes of RAM for immediate calculations and tens of petabytes of storage. By using insanely complex parallel file systems like Lustre, GPFS, or BGFS, millions of files can be written simultaneously without the whole system crashing. It is a literal symphony of synchronized hardware. So, what does this all mean for us? We've explored the unimaginable scale of Frontier, El Capitan, those Sunway prototypes, and that shared Linux DNA running the whole show. But honestly, the tech is only as important as what we do with it. As these machines push deeper into the exascale era and beyond, what will be the next great breakthrough driven by these giants? Will it be a perfect, flawlessly accurate climate model, the cure for a currently untreatable disease? Or maybe an AI that fundamentally shifts how we understand the universe? The machines are ready and waiting. Now it's up to human ingenuity to ask the right questions. Thank you so much for joining me on this explainer. Keep wondering, keep questioning, and I'll catch you next time.